name is Stuart Kauffman, and I'm very pleased to have the chance to talk today under the title, What is Life? Answering Schrödinger. There's a lot of material in this talk. It's all text. I will be reading it. The material will be available online in some form or another soon. Next slide. My purpose in this lecture is to discuss quantum physicist Erwin Schrödinger's superb book, What is Life?, published in 1944. The answer he gives and the very large problem with which he leaves us. I will put this in a larger framework of the emergence and evolution of life on Earth from 3.7 billion years ago and the vast evolutionary flowering of complexity in the biosphere. Or as Darwin said at the end of Origins of Species, from so simple a beginning. Next slide. Some references. What is Life by Schrödinger, Cambridge University Press, 1944. Complexity in the Arrow of Time, Lineweaver, Davies and Roos, Cambridge UP, 2013. From Matter to Life, edited by Walker, Davies and Ellis, Cambridge University Press, 2017. Next slide, please. Origins of Order, Self-Organization and Selection and Evolution, Stuart Kauffman, Oxford UP 1993. Investigation, Stuart Kauffman, Oxford UP 2000. A World Beyond Physics, The Emergence and Evolution of Life, Stuart Kauffman, Oxford UP 2019. An Incomplete Nature, How Mind Emerged from Matter, Terence Deacon, W.W. Norton. Next slide, please. In What is Life?, Schrödinger does not ask what life is or how life emerged from non-life, then evolved. I'll make proposals below. Schrödinger asks two major questions. First, what is the source of order in organisms? And second, how do organisms remain ordered in the face of the second law of thermodynamics? I shall propose that Schrödinger's answer to the first question, his famous aperiodic solids, is also the still unarticulated answer to his second question. Next slide. Towards the aperiodic solid. Schrödinger notes that there is a source of order from disorder in well-known 19th century physics seen in statistical mechanics. For example, the diffusion of a drop of milk in a coffee cup to a uniform mixture at equilibrium. Diffusion yields order from disorder. He notes that the basis for this macroscopic order is chaos in the random motions of the atoms. Then Schrödinger notes that as the number of molecules in the system is reduced, the system becomes more random. Macroscopic order from disorder depends upon a large number of atoms. Next slide, please. He next considers recent evidence from the X-ray induction of heritable mutations in, I think, Drosophila, that the hereditary material, genes, can have only on the order of 1,000 atoms. Thus, order from disorder cannot explain the order in organisms. He concludes that the order in organisms must be due to quantum mechanically stable molecules, which are stable despite having only a small number of atoms. Next slide. Schrödinger then brilliantly concludes that the solid will not be periodic, like quartz, for these are, as he says, dull. Rather, the hereditary material would be an aperiodic crystal that contains, in some kind of code script, the entire pattern of the individual's future development. The code script will be efficacious in bringing about the organism. Here's what he says. In physics, we have dealt hitherto only with periodic crystals. To a humble physicist's mind, these are very interesting and complicated objects. They constitute one of the most fascinating and complex material structures by which inanimate nature puzzles his wits. Yet compared with the aperiodic crystal, they are rather dull. The difference in structure is of the same kind as that between an ordinary wallpaper in which the same pattern is repeated again and again in regular periodicity, and a masterpiece of embroidery, say a Raphael tapestry, which shows no dull repetition, but an elaborate, coherent, meaningful design traced by the great master. Next slide. He continues, it is these chromosomes that contain in some kind of code script the entire pattern of the individual's future development and of its functioning in the mature state. Every complete set of chromosomes contains the full code. Next slide. It is Schrödinger's truly brilliant intuition that an aperiodic solid, which contains in some kind of code script the entire pattern, that inspired Watson and Crick in their 1973 discovery of the structure of DNA, which Avery had recently shown to be the genetic material. DNA is precisely an aperiodic solid. In the next decades, the existence of the genetic code was deduced and worked out. Thus, Schrödinger concludes, the order in organisms does not come by order from disorder, as in diffusion, but by order from order. Next slide. Schrödinger's second question. How do organisms remain ordered in the face of the second law of thermodynamics? Quotes, how would we express in terms of the statistical theory of statistical mechanics that the marvelous facility and faculty of a living organism by which it delays the decay into thermodynamical equilibrium, death? The device by which an organism maintains itself stationary at a fairly high level of orderliness really consists in continuously sucking orderliness from its environment. Schrödinger's use of the phrase sucking orderliness from its environment is also called negentropy. It is really this question that I'm going to tackle in this discussion. Next slide, please. Critically, Schrödinger does not see how his second question is answered by the known laws of classical and quantum physics. Quotes, we must therefore not be discouraged by the difficulty of interpreting life by the ordinary laws of physics, for that is just what is to be expected from the knowledge we have gained of the structure of living matter. We must also be prepared to find a new type of physical law prevailing in it. Or are we to determine a non-physical law, not to say a supra-physical law? Next slide. I'm going to turn to a next topic that relates to Schrödinger's question. Schrödinger did not know about dissipative structures, and part of the answer to Schrödinger's second question is already contained in his phrase, really consists in continuously sucking orderliness from its environment. In systems displaced from equilibrium by the flow of matter and energy through them, namely sucking orderliness from the environment, macroscopic patterns can emerge. Dissipative structures were unknown when Schrödinger wrote in 1944. Ilya Prigogine and his group led a large effort to study the onset of ordered patterns in far from equilibrium physical and chemical systems and termed such patterns dissipative structures because they dissipate free energy. Examples include whirlpools, tornadoes, hurricanes, Bénard cells, and the Bielosov-Zhabotinsky reaction. The giant red spot on Jupiter is a fine example. Next slide. In these systems, the macroscopic pattern emerges as energy flows through the system, which is therefore displaced from equilibrium by that energy flow. The Bénard cell is an instructive example. Here there's a pan with a shallow layer of a viscous liquid, for example, oil. The pan is heated slowly from below, creating a temperature gradient, hotter on the bottom than the top of the fluid. When the temperature gradient induces an overall heat flow to the environment, the temperature does. But when the gradient is small, the heat flow to the environment is achieved by conduction of random motions of the oil molecules. When the temperature gradient surpasses the Rayleigh threshold, convective cells arise and dissipate heat more effectively. The convective cells are called Bénard cells. Next slide, please. Bénard cell patterns are sustained by the continuous flow of energy through the system by heating the pan from below. Now, this is the important next step. The form of these cells depends upon the boundary conditions created by the shape of the pan, whether it's a square pan, a rectangular pan, or a circular pan, or so forth. The Bénard cells could be hexagonal or rolls. Critically, if the shape of the pan, i.e. the boundary conditions, are changed, so too are the shape and overall pattern of the Bénard cells. This is all worked out in great detail. Next slide. The beginnings of an answer to Schrödinger's second questions. I propose below that Schrödinger's aperiodic solid that constitutes a code script that is effective for the formation of the organism is because the aperiodic solid is one or a set of boundary conditions that thereby control the dynamics of the non-equilibrium system in living cells and organisms. Thus, as we'll see in more detail below, Schrödinger's answer to his first question is the answer to his second question, but it will take a time to make this clear. Next slide. I turn now to thermodynamic work and boundary conditions. This will take us beyond the limitations of dissipative structures. Dissipative structures such as hurricanes, whirlpools, and Bénard cells do not become very complex and increasingly diversified in their complexity. By contrast, the evolution of life started with rather simple protocells, followed by simple single-cell organisms such as archaea and eubacteria, then eukaryotes, then multi-celled organisms, then the Cambrian explosion 550 million years ago, with the flowering of some 30 extant phyla to millions of distinct species today, bacteria to whales, and redwood trees in an open-ended evolutionary avalanche of becoming. What is the difference between dissipative structures and evolving life? Well, of course, many things are, but next slide, please. Part of the reason the dissipative structures do not become indefinitely complex is that they do not construct their own boundary conditions. Organisms, as we shall see, do construct their own boundary conditions and do so by carrying out thermodynamic work to construct those very boundaries. Next slide. Work constraints and the work constraint cycle. You can find some of this in my book, Investigations, Oxford University Press 2000. Work is force acting through a distance, says Newton. But Atkins, in his book on the second law of thermodynamics, says something that will be fundamental to us. Work is the constrained release of energy into a few degrees of freedom. Degrees of freedom means what the possibilities are. So work is the constrained release of energy into a small number of what's possible. Let's consider as an example a cannon and a cannonball inside the cannon. The explosion of the powder releases energy into the few degrees of freedom left as created by the cannon itself, which constrains the release of energy into those few degrees of freedom so that the cannonball can only move down the cannon shaft. Thermodynamic work is done on the cannonball. The powder explosion is exergonic, the release of free energy. The resulting movement of the accelerated cannon is endergonic. It takes the absorption of free energy. When the powder explodes, part of the energy is dissipated as heat, producing entropy. But part of the released energy does thermodynamic work to propel the cannonball. Next slide. Critically, were the cannon not present and the powder exploded on a flat plate next to the cannonball, the ball would hardly move and most of the energy would be dissipated as heat, thereby producing more entropy and less work would be done. Thus, the constrained release of energy that does work in linked exergonic endergonic processes produces work and at the same time produces less entropy than were the constraints not present. This is going to be central to us. The point's fundamental. When more work is done in the constrained release of energy in a non-equilibrium process, less entropy is produced in the process than were the process less constrained. This will be a central part of our answer to Schrödinger's second question. Next slide. Propagating macroscopic thermodynamic work. In an automobile, the explosion of gas causes the piston to move, which causes the crankshaft to turn, which causes the wheels to turn. Thermodynamic work propagates in a coupled set of exergonic and endergonic processes from the gas explosion to the wheels turning. Let me define this as propagating work. A large number of macroscopic changes happen in the world. The canon, which constitutes the constraint on the release of energy into a few degrees of freedom, is a boundary condition. Similarly, in an automobile, the cylinders, the pistons, gears, escapements are boundary conditions on the release of energy from the exploding gas into a few degrees of freedom that constitutes propagating thermodynamic work by which the engine leads to the physical motion of the car on the road. But I'm going to come now to a new question. Where, since the Big Bang, or in the last 100,000 years, did the cannon or the cylinder and piston boundary conditions come from? Next slide. After the Big Bang, for example, in the last 100,000 years, thermodynamic work was required to construct the cannon, the cylinders and the pistons, the gears and the escapement. It takes work to construct constraints. And this leads to the work constraint cycle, which is in my investigations 2000. No constraints, no work, but also no work. Typically, you don't get any constraints. It takes work to make constraints. Next slide. So this is the work constraint cycle. I don't think you'll find it in the physics books, but I'm pretty sure it's true. In our human machines to date, we organize the work to construct structures, often low energy stable structures, such as cannons and pistons, that are then used as boundary conditions on the release of energy to a few degrees of freedom, such that propagating thermodynamic work is done. Engines turn over and cars move. So again, since the Big Bang, where do boundary conditions come from? Well, it takes work to make the boundary conditions. We will see below that cells and organisms do thermodynamic work to construct their own boundary conditions. Cells do not construct their own boundary conditions. The machines we make do not construct their own boundary conditions. Cells do. Next slide. New but related topic. In classical physics, the boundary conditions can vary freely and can carry a causally effective code script. This is the next step in answering Schrödinger. Newton's framework for classical physics are his laws of universal gravitation and his three laws of motion, coupling the variables in differential equation form, plus initial and boundary conditions, which are not themselves specified in the laws of motion. Using the initial and boundary conditions, we integrate the differential equation laws of motion to obtain the entailed trajectories of the variables, for example, billiard balls moving on a billiard table. The boundary conditions determine what the phase space of the system is. For example, on a billiard table, the boundary conditions given by the table boundaries thereby specify all possible positions and momenta of the balls on the table. But the set of all possible positions and momenta constitutes the phase space of the system. Next slide. Keeping the boundary conditions the same and altering the initial conditions of the balls alters the trajectories of the ball in the same phase space. But altering the boundary conditions, for example, the shape of the billiard table from square to round, alters the very phase space of the system. But Newton's laws leave free what the boundary conditions might be. Next slide. A simple example is the Pee Wee golf course I visited recently here in Santa Fe. It consisted in 18 holes. Each hole was created by arranging 6 by 6 inch timbers on the ground in various arrangements. For example, the major timbers were parallel to one another, creating pathways, then turned corners at various angles. Short timbers were arranged jutting out into the pathways the parallel boards created. The golf ball, once hit, caromed off the jutting short timbers in complex ways. The short timbers and also the long timbers are boundary conditions. Next slide. If the short timbers are rearranged, the motion of the golf ball after it is hit will change. But we are free to arrange and rearrange the short timber boundary conditions in many ways. For such a timber to carry information, it is essential that the timber could counterfactually have been located in a different way. This counterfactual captures we are free to rearrange the short timbers. Rearranging the timbers in some arbitrary way alters the phase space of the system in some arbitrary way. We will see below that for Shannon's bits to carry information in Shannon information theory, it is also essential that counterfactually the bits could have been otherwise. Next slide. Pre-summary. Rearranging the timbers in some arbitrary way alters the phase space of the system in some arbitrary way. In evolving organisms with DNA, RNA, and encoded protein synthesis, these molecules are all aperiodic solids that, as we will see, constitute boundary conditions on the constrained release of energy in myriad enzyme-catalyzed chemical reactions into a few degrees of freedom that does thermodynamic work to construct further and often changing aperiodic enzymes that are further boundary conditions. In cells, thermodynamic work is done to synthesize RNA and proteins. The new RNA and protein sequences are new boundary conditions, and their construction persistently changes the various phase space of the cell and organism. Next slide. In particular, cells have genetic regulatory networks in which thousands of genes turn one another on and off. So different cell types make different combinations of proteins. Each protein is a boundary condition. So different cell types expressing different proteins that are boundary conditions live in different phase spaces. In single-cell organisms over the life cycle, the RNA and proteins present change. These changing RNA and protein sequences contain causally effective information that creates different phase spaces. This causally effective information is Schrödinger's causally effective code script. Next slide. Let's go through this more slowly. The critical step I now take is to identify Schrödinger's code script, to which Schrödinger points, that are the very boundary conditions constituted by the aperiodicities in the aperiodic solids in a living cell. A specific example is a hereditary DNA molecule with, in this case, the aperiodic sequence of nucleotide bases, A, T, C, and G. Next slide. The sequence of bases A, T, C, and G in the DNA are indeed boundary conditions. DNA is transcribed into RNA, in the simplest case, into messenger RNA, A, U, C, and G. That RNA sequence is loaded with 20 different encoded amino acids via specific transfer RNAs, each of which binds a specific amino at its amino acid binding site and binds the RNA sequence's codon via the transfer RNA's anticodon site. Specific encoded synthetase enzymes attach the proper amino acid to its proper transfer RNA. As the RNA is so loaded, it is processed by the ribozyme to link the amino acids into a growing peptide by forming peptide bonds. Work is done at each step utilizing the degradation of ATP to ADP as new bonds are formed. This is just familiar cellular biochemistry and the central thesis of molecular biology. Next slide. At all steps, one or more molecules act as boundary conditions on the reaction occurring. For example, the single-stranded DNA molecule uses Watson-Crick bonding to bind and line up adjacent free A, U, C, G nucleotides of the growing RNA molecule. By so binding these free RNA nucleotide bases, their three-dimensional freedom to diffuse is confined to one dimension, thereby lowering the activation barrier to form the proper 3', 5' phosphodiester bond between the adjacent RNA nucleotides. In forming those bonds, thermodynamic work is done using ATP degradation to ADP as the energy source, and a new chemical bond is formed. In short, the single DNA strand acts as a boundary condition enzyme binding the substrate RNA bases, lowering the activation barrier, enabling the chemical energy of the ATP to be released into a few degrees of freedom, thus forming that specific 3', 5' phosphodiester bond between the two RNA nucleotides, rather than the thermodynamically more favorable 2', 5' bond. In short, energy is released into a few degrees of freedom due to the boundary condition constituted by the single-stranded DNA molecule. Next slide. The DNA, RNA, and encoded proteins carry information, but they could counterfactually have been different. This arises both in evolution by mutation and recombination and in changing patterns of gene expression in single cells and during development of multicell organisms with cell differentiation. So I'm saying this for a second time, but we must be very clear about it. In evolution, the sequence of bases A, T, C, and G counterfactually could have been different. for an ontologically indeterminate quantum mutation event could have happened and could, say, convert an A to a G. This mutation freely rearranges the nucleoside sequences in the base, which is to freely arrange the boundary conditions. The freely rearranged DNA sequence via the ontologically indeterminate mutations constitutes a new boundary condition that encodes information because it is a boundary condition, so causally efficacious and counterfactually could have been different had the mutation not occurred by a random quantum event. Next slide. I conclude that Schrödinger's code script is causally efficacious and includes the DNA, RNA, and proteins that act efficaciously as freely changeable boundary conditions. Of course, other features of cells, such as cell membrane, organelles, microtubules, and so on, are also boundary conditions. Next slide. Thus, the code script is written in a changeable set of boundary conditions that allow thermodynamic work to be done and catalyze chemical reactions in different specific ways, even as entropy is created and released. But if in the release of energy is more constrained, more work is done, and less entropy is produced than the release of energy less constrained. Life sharply constrains the release of energy to do more work, and so less entropy is produced than otherwise. This is the central part of how life surpasses mere dissipative structures and copes with the second law of thermodynamics, to say organized even though an open system in the face of the second law. Schrödinger's answer to his first question, aperiodic solids, again, answers his second question. Next slide. I'm turning now to a new topic, but they're all related. The Hard Problem of Life by Sarah Walker and Paul Davies in their book, From Matter to Life, which I'll refer to again, but I refer to up above. To be clear about the issues that Walker and Davies discuss requires being clear about what in physics is meant by a macrostate. This derives from statistical mechanics. Consider a liter box with a single particle in it. The position of the particle in the box can be specified by three numbers, giving its position on the three spatial axes of the box. The momentum of the particle, mass times velocity, can be given by three numbers, saying how fast it's moving in each of the three dimensions. So 6 numbers specify the position and momentum of the particle. Thus, for n particles, 6 n numbers must specify the positions and momentum of all n particles at any moment. This 6n dimensional volume is the phase space of the system of all possible positions and momenta of the n particles. Therefore, in a 6n dimensional phase space, a single point is a simultaneous position of and momenta of all n particles. A macrostate is a box of 6n dimensions, a small box, in the 6n dimensional phase space. The total volume of the phase space is entirely filled by these small 6n dimensional microstates, rather like ice cubes would fill a 3-dimensional box. So the ice cube is a microstate. Next slide. The size of the microstate 6n volume could be large or small, a large or small ice cube, and that's our free choice, and it's called coarse graining. Large volume microstates are large coarse graining, small volume microstates are fine coarse graining. Now we need a macrostate. A macrostate is any set of 2 or more microstates. For any system with a large n, there are vastly many possible macrostates. The entropy of a macrostate is defined as the logarithm of the number of microstates in that macrostate. So if the macrostate has 100 microstates, the logarithm to the base 10 is 2. If it's got 1,000, the logarithm to the base 10 is 3. Statistical mechanics builds from these via the ergodic hypothesis, which says that equal volumes of phase space will be occupied equally. This yields the second law of thermodynamics, in which entropy tends to increase, and in a closed system tends to go to a maximum at thermodynamic equilibrium, for example, the homogeneous coffee milk mixture after diffusion. This is Schrödinger's order from disorder. By the way, the ergodic hypothesis, equal volumes of phase space will be occupied equally, gives up integrating Newton's equations, and in that sense it's acausal, and that's why the claim is a tendency based on the ergodic hypothesis. Anyway, this is Schrödinger's order from disorder. Next slide. Walker and Davies seek to state what they call the hard problem of life. How is information causally efficacious in organisms? Quotes, the challenge is that we do not have a physical theory for information that it might explain how information calls the shots. The hard problem of life, page 33, in From Matter to Life, 2015, edited by Walker and Davis and George Ellis, Cambridge University Press. Next slide. Walker and Davies continued. In particular, we posit that the manner in which biological systems implement state-dependent dynamics is by utilizing information encoded locally in the current state of the system, that is, by attributing causal efficacy to information. By state-dependent, they mean that the state of the system is somehow controlling the macro state, which we'll get to now in a second. It is widely thought that coarse graining, which would define the relevant informational degrees of freedom, plays a fundamental role in how biological systems are structured. However, it is not clear how those macro states arise. The macro state is the relevant informational degrees of freedom. It is not clear how those macro states arise, or whether they are in fact fundamental aspects of biological organization intrinsic to the dynamics, i.e. that such macrostates are causal. A framework in which coarse-grained information encoded in encoding macrostates are causal holds promise for resolving many of the problems discussed herein. This is the key aspect of the hard problem. Walker and Davies, The Hard Problem of Life, From Matter to Life, Walker, Davis, Ellis, Oxford University Press, 2015. It's Cambridge University Press. I'm looking at the book. Next slide. I believe that the issues confronting Walker and Davies is that a macro state can be any combination of the possible microstates in the total system. So if there's 1,000 microstates, there's all the subsets of them that you can choose, and that's on the order of 2 to the 1,000. The number of particles in the universe is 10 to the 80th. Then how can some choices of macrostates be causally efficacious? I'm going to propose that there is at least one set of possible macrostates that is one straightforward answer to the hard problem of life. Walker and Davies have not criticized this, and it will be important to hear what they say. The relevant macrostates to which Walker and Davies refer are precisely the specific arrangement of atoms that constitute the aperiodic solids that are boundary conditions present in cells, such as the specific aperiodic DNA sequences and time-varying aperiodic RNA and protein sequences present in a cell that are boundary conditions, as discussed above, directing which catalyzed reactions occur that direct the constrained release of free energy in specific directions, thus doing thermodynamic work and by linking exergonic and endergonic processes, degrading ATP into ADP. Next slide. Next slide, please. Next slide. The boundary conditions here are indeed state dependent and encoded locally. It's in the current state of the cells, namely what RNA and protein sequences are being synthesized. As the RNA and protein sequences in the cells change over time or between cell types or in evolution, the boundary conditions change, hence do so in a manner that depends upon the aperiodic crystal boundary condition state of that cell. These boundary conditions constitute the macrostates that are relevant information degrees of freedom and are, as classical physical boundary conditions, causal. Let me enlarge on that for a moment. Suppose that you took a protein molecule with 400 amino acids in it, and you dissolved it into its amino acids, or the atoms of which the amino acids are made, in a liter box of water. So the relevant phase space is a 6n-dimensional phase space constituted by those atoms. A particular macro state is one in which those atoms are all joined together to make that protein. So that protein is in fact a relevant macro state that's an informational degree of freedom. The protein is in fact a subspace of the 6n-dimensional phase space of its particles. So now to the last point, using varying boundary conditions, here RNA and proteins as embodied information, clearly allows information to call the shots. Next slide. New topic. We've already said it briefly, but let's come back to it and say it in detail. Work versus the production of entropy. Consider again the cannon and the cannonball. The cannon boundary conditions yields the constrained release of energy when the powder explodes, thrusting the cannonball out the cannon. But were the cannon not present, the powder explosion would have produced more entropy and less work than if the cannon is present, where less entropy is produced and more work is done. Thus, in general, work is the constrained release of energy into a few degrees of freedom. If the constraints increase so that energy is released into fewer degrees of freedom, more work is done and less entropy is produced. Next slide. This is how, in answer to Schrödinger, life copes with the second law. Highly constrained release of energy into very few degrees of freedom occurs, which work is done in cells. That work constructs the boundary conditions on the release of energy into a few degrees of freedom that constitutes work. Some of the work done constructs the very same set of boundary conditions. In a moment, we will see that this is constraint closure. As these processes occur, each does more work and produces less entropy than were the constraints fewer, so that less work would be done and more entropy produced. Next slide. As we will see, this is how life copes with the second law to produce a sustained state of order in a volume of space and time in living cells. Again, thus Schrödinger's answer to his first question, aperiodic solids, is the answer to his second question. Next slide. I'm turning to information, entropy, and work as the constrained release of energy into a few degrees of freedom. Schrödinger wrote in 1944. Later in 1948, Shannon invented information theory. The concept of information has been very powerful and used in many ways. Consider, for example, a Van Gogh painting. The painting could be partitioned into 10,000 square pixels, and the color of each square encoded in 10 bits. So the information of the pixel of the painting is encoded in 10,000 times 10, or 100,000 bits. So far, this information is not efficacious in the actual world. But the information is physically encoded in bits on a computer, and they can then be used to send the computer to a printer to print out a copy of the painting. So part of our puzzle is that just as an encoded description of the painting, so far the information is not causally efficacious. Next slide. Soon after information theory was invented, biologists wondered if the zygote was a chemical channel to convey information from the parents to the offspring. It was soon learned that the zygote could not encode sufficient information to specify the newborn. The zygote is not a channel. With respect to Maxwell's demon, the demon uses information to defeat the second law. Szilard and later Landauer and Wojtek Zurek showed that the demon could not win in a closed system, saving the second law. Next slide. I want to explore a causally efficacious sense of information. Shannon conceived of information as based on uncertainty, where a message received would lower the uncertainty of the message sent from the source down a noisy channel to the receiver. Among others, Davies in The Demon in the Machine makes his point about information as the reciprocal of uncertainty. Shannon defines the entropy of an ensemble of messages at the source. It's a sum p log p, where p is the frequency of a given message. The information sent down the noisy channel and received is reduced entropy or increased certainty at the receiver about the message sent. Next slide. So received information reduces uncertainty. Shannon's equation for information is the negative of Boltzmann's mathematical expression for entropy. Thus, as entropy increases physically, information decreases and vice versa. This is a crux. To carry information, the message must counterfactually have been able to be different. If not, for example, if the only message is 111111111, its entropy is 0 and it carries no information. Now, consider work as the constrained release of energy into a few degrees of freedom. Picture the cannonball and powder exploding between the ball and the base of the cannon. Work is done blasting the ball forward with less production of entropy than were the cannon not there. Next slide. Then consider instead the cannonball on a flat steel plate lying exactly on top of the pile of powder. Let the powder explode. The flat steel plate confines the motion of the cannonball less than does the real cannon. So in the flat steel plate case, the energy is released into more degrees of freedom than in the real cannon case. In the real cannon case, with the release of energy into fewer degrees of freedom, more work is done and less entropy is produced than in the flat steel plate case. And there is less uncertainty, hence more information, in the outcome of the real cannon process than in the flat steel plate case. Next slide. Just for amusement, in between the real cannon case and the flat steel case, it is amusing to consider a tuba-shaped cannon. Here, the direction of the cannonball takes when shot from the tuba cannon is more certain than in the flat steel plate case and less certain than the real cannon case. The tuba cannon produces more work, less entropy, and is more informed than the flat steel case, and produces less work, more entropy, and is less informed than the real cannon case. Next slide. In summary, as the constraint boundary conditions on the release of freedom, on the degrees of freedom into which energy is released increases, more work is done, less entropy is produced, and the outcome is less uncertain, so more informed or more full of information. This constrained release of energy does work, so the informed process calls the shots and has causal efficiency and efficacy. This is not limited to mechanical work. Any non-equilibrium thermodynamic process that is constrained in the release of energy into fewer degrees of freedom does more work, produces less entropy, and is more informed or carries more information than were less constrained. This work can be harnessed into propagating work with many macroscopic changes in the world, and automobile is an example. Next slide. We turn to the next topic, due to Mael Monteville and Matteo Mosio. We saw above that thermodynamic work can be done to construct structures. But this means that thermodynamic work can be done to construct structures that are themselves available to be used as boundary conditions, that is, as constraints. The constructed release of energy, the constrained release of energy can construct more constraints. Machine tools can construct cylinders that are themselves able to be used in the automobile engines as constraints on the release of energy to do work to power the car. Next slide. Mael Monteville and Matteo Mosio introduced the concept of constraint closure in 2015. In a constraint closed system, there is a set of non-equilibrium processes, 1, 2, 3. Each is constrained by a set of constraints, A, B, C, such that the constrained set of processes, 1, 2, 3, does thermodynamic work to create the very same set of constraints, A, B, C. For example, process 1, constrained by A, constructs B. Process 2, constrained by B, constructs C. Process 3, constrained by C, constructs A. That's a constraint closed system. Next slide. I think Mael Monteville and Matteo Mosio have found an absolutely remarkable concept. I think it may be a central concept of biological organization. This constraint closed system is remarkable. It is an open thermodynamic system carrying out a cycle of thermodynamic work with the formation of entropy. The entire system constructs the very constraints on the release of energy by which the work is done to construct the very same constraints. It takes a while to get one's mind around this, and then you see that it's just beautiful. Because the release of energy is constrained, more work is done and less entropy is produced than were the release of energy less constrained. These constraint closed systems, far from equilibrium process, are organized. A non-mystical holistic closure is achieved in the system above. No constraint constructs itself. The set of non-equilibrium processes and constraints mutually construct the joint set of constraints by linking the set of non-equilibrium processes into a closed set of work tasks to be jointly performed. Next slide. We're on to life itself now. There are several theories for the origin of life. These include the most famous RNA world, which is the idea, well, I'll get to it in a minute, and the theory of the spontaneous formation of collectively autocatalytic sets, CAS, of RNA, of peptides, and of lipids. People who've talked about this are Diemer in 2019, Davis in 2019, and me in 2019. I actually originated the theory of autocatalytic sets and published it in 1971 and in 1986 and so on. In the RNA world, the proposed template set for replicating RNA has not yet been found, but it may be found experimentally. Autocatalytic sets of DNA, of RNA, and of proteins, and of lipids have in fact been created. Since sets of peptides can collectively reproduce, Gonan Ashkenazi has a 9-peptide set, molecular reproduction does not require nucleotides. This means that the RNA world may be true, but it is not necessary, if not for life, at least for molecular reproduction. Next slide. Such collectively autocatalytic sets, for example, peptides, or RNA or both, like Gonan Ashkenazi have, achieve constraint closure. It would take me a moment to show you this, but the peptides or RNA constituents are enzymes, which are boundary conditions on the very reactions by which the same peptides or RNA enzymes are formed. Kauffman 2019. In this process, thermodynamic work is done to construct the peptides, which themselves are the boundary conditions on the release of energy into few degrees of freedom. Entropy is produced in this non-equilibrium process, but less than where there are no or less constraints on the release of energy. This again answers Schrödinger's second question. Collectively autocatalytic sets, where the catalysts are themselves boundary conditions, constrain the release of energy into few degrees of freedom, doing a lot of work and not producing too much entropy, therefore remaining ordered in the face of the second law. Next slide. These collectively autocatalytic sets achieve 3 closures: constraint closure, work task closure, and catalytic closure. By the latter, I mean that every reaction that needs to be catalyzed is catalyzed by some member of the set. Same thing for constraint closure and work task closures. The set of 3 closures is a non-mystical holism. Thanks to the 3 closures, such systems literally do thermodynamic work to construct themselves. This is very fundamental. Cells construct themselves. They don't describe themselves. Next slide. On to evolving protocells. Several theories exist which house such collectively autocatalytic molecular sets in liposomes that divide, creating protocells. See, for example, Roberto Serre, 2017, Damer and Diemer, 2019. I described the Damer-Diemer scenario as something of Serre's in my 2019 book. Whether formed of DNA, RNA, or peptides, all these are aperiodic solids, and as enzymes can act as boundary conditions in non-equilibrium systems on the release of energy into a few degrees of freedom to do thermodynamic work with the simultaneous creation of less entropy than were the constraints not there. Such systems can exhibit heritable variations carrying a code script that is causally efficacious. Next slide. Walker and Davis, this is a new topic. Walker and Davis, 2013, Royal Society, call either reproducing collectively autocatalytic sets or sets self-templating nude RNA trivial reproducers. They make a major point. Trivial reproducers do not yet marry collectively autocatalytic set peptides or metabolic autocatalyc sets reproduction and reproducing nucleotides to one another and also to nucleotide encoded synthesis of proteins. This union would be the origin of non-trivial reproducers and the origin of life. Next slide. Walker and Davies pointed out something very interesting, that encoded protein synthesis realizes von Neumann's universal constructor for the space of all possible proteins built of the standard 20 amino acids. By mutation, recombination, horizontal gene transfer, and so forth, the evolving biosphere can explore the vast space of never-before-born possible RNA and protein sequences. These, in turn, can have functions in cells. Next slide. Open-ended upward, open evolution upward in complexity. So this is a very important point. The universe is non-ergodic above the level of atoms. Namely, since the Big Bang, all stable atoms, 120 of them or so, or 100 have been made. But most complex things will never come to exist. The universe has not had times, and hundreds of trillions of times the lifetime of the universe, to make all possible proteins with 200 amino acids in them. Thus, and this is physically important, there's an infinite sink upward in complexity that evolution can explore. Thereby, life undergoes an ever open-ended evolution. Protocells give rise to bacteria and archaea, to eukaryotes, to sex, to multicellular organisms, to the Cambrian explosion and 13 phyla. All this is propagating, self-organizing, self-constructing of non-equilibrium processes into the indefinite diversity and complexity upward in the indefinite hierarchy of the open non-ergodic universe above the level of atoms. This explosion is into the adjacent possible of the evolving biosphere. Next slide. Let me define the adjacent possible. The adjacent possible is what can possibly arise next, and it arises out of what is actual now. Given fish, amphibians are in the adjacent possible of the biosphere. Given Apollo, the space station is in the adjacent possible of the econosphere. All of this arose from the Big Bang. As someone said, from the Big Bang, somehow we got to New York. Next slide. We have to talk about where the free energy for all of this comes from. The free energy for this evolution to occur is based on a low entropy state of the very early universe. It's in some uniform state, homogeneous state, and the accelerating expansion of the universe. Thus, the maximum entropy of the universe is growing faster than the actual entropy, so that the gap between them, which is the free energy, is always available to do thermodynamic work using the open-ended evolution of the biosphere. Lineweaver discusses this in Complexity in the Arrow of Time, and that's the book, Lineweaver, 2013. But the availability of free energy is only a necessary condition, not a sufficient condition for the vast emergence of complexity in the universe since the Big Bang. Biospheres on Earth, or among the 10 to the 22 solar systems in the universe, construct themselves up into exploding diversity and complexity in a non-ergodic universe above the level of atoms. Next slide. Next, I want to say that neither quantum mechanics nor classical physics alone or together explain the evolution of the biosphere. So I'll repeat myself. Neither quantum mechanics or classical physics alone or even together explain the evolution of the biosphere. Mutations, say in Drosophila melanogaster, are random quantum events occurring in the fly's DNA. These random events counterfactually change the DNA code script boundary conditions by which the organisms construct themselves as open thermodynamic systems. The random mutation may create a DNA molecule, now effectively classical in the fly, as is the fly itself, but the mutation might render the fly with the mutation fitter than before. For example, the mutation might cause the eye to be white rather than red, and let it now be, for example, a dominant mutation. Due to natural selection, soon millions of copies of that DNA molecule causing white eyes flies will exist in the non-ergodic universe above the level of atoms, all over our biosphere. Next slide. Longo, Mondeville, and Kauffman, 2012, have demonstrated that no laws entail the evolution of the biosphere because we cannot prestate the ever-changing phase space of open-ended evolution. So we can neither write laws of motion nor integrate the laws that do not exist. Thus, no laws entail the evolution of the biosphere. Reductionism stops at the watershed of life. Thus, neither quantum mechanics or classical physics alone or together suffice to account for the specific evolution of the biosphere, which is bond-entailing laws. Thus, as noted, the universe is non-ergodic above the level of atoms. Most complex things will never get to exist, so the coming into the existence in the universe of the mutated DNA molecule in a population of Drosophila melanogaster is unentitled and unexplained. Quantum mechanics and classical physics alone or together fail to account for the existence of this DNA molecule on planet Earth. There is no final theory. Reductionism ends at the watershed of life. Next slide. And last topic. A very tentative fourth law of thermodynamics. The adjacent possible of the universe tends to increase. The universe grows into the growing adjacent possible. It itself creates as it becomes more diverse. This is my third try trying to state what might be such a law. Next slide. The first law of thermodynamics states that energy is conserved. The second law of thermodynamics states that the entropy of a closed or open system tends to increase. Again, this mere tendency arises because the aerobatic hypothesis gives up integrating Newton's equations and tail trajectories of the vastly many particles in the 6n phase space, and instead asserts non-causally that the system will spend equal time in equal volumes of the 6n phase space, hence tends to flow or be in macrostates with more microstates. The third law of thermodynamics, based on the equivalence of heat and average kinetic energy particles, states that there's a zero temperature, 0K, at which molecular motion stops classically. On quantum mechanics, of course, there are 0-point fluctuations. Next slide. Here's a very crude view of the evolution of the universe since the Big Bang, spatially and in kinds of matter. Quark glue on soup may be 10 to the 12th K temperature. Formation of a zoo of subatomic particles of matter and antimatter. Matter wins. Protons, neutrons, and electrons form. These give rise to atoms like hydrogen and helium very early. Then nucleosynthesis of the heteronuclei in atoms and stars. For example, carbon is built from 3 helium nuclei. The formation of simple and complex molecules in space chemistry. Already this is non-ergodic. Not all complex molecules can be created in the lifetime of the universe. The Murchison meteorite has 14,000 organic molecules and was created 5 billion years ago. The expanding cooling universe, inflation and beyond, gravitational contraction, increasing gravitational entropy, hydrogen, helium, patchy gas clouds, cosmic background radiation, galaxy stars, planets, and later life and biospheres among the 10 to the 22 predicted solar systems. The origin and open-end evolution of life upward into the infinite sink or indefinite sink of increasing complexity in the non-ergodic universe. Next slide. The adjacent possible of the universe is what can arise next, given what is now actual in the quantum cum classical and abiotic biosphere, evolving beyond entailing law worlds. Given the free energy that is persistently available, the universe creates increasing diversity of processes and things that create and invade the growing adjacent possible. These processes themselves create. A very tentative fourth law of thermodynamics. The adjacent possible of the universe tends to increase. The universe grows into the growing adjacent possible. It itself creates. Next slide. We have covered a lot. I thank you for your attention, and I thank you for interest in the whole topic.